Hello students, in this video we'll see an example of changing the order of integration on a double integral. Let's compute the integral from 0 to 1, the integral from the third root of x to 1 of e to the fourth power of y, then we'll do a dy dx. And so what we should note is we note that the integral, so note the integral of just e to the y to the fourth dy cannot be expressed by elementary functions. In other words, I can't write this antiderivative in terms of exponentials, trigonometric functions, hyperbolic functions, polynomials, anything that we're used to seeing. So I can't actually perform this integration without introducing special types of functions, namely exponential integral class functions. So this is an integral we can't actually find an explicit antiderivative of, so it seems like we can't do this problem because we're first doing a y integration. However, if we sketch the region of integration, we know that x goes between 0 and 1. So let's write down our xy axis. There's my x-axis, my y-axis. X goes between 0 and 1. And I'm going to plot this curve over here and figure out where y goes between. So y starts on this curve, the third root of x. So if y is equal to the third root of x, then that curve looks like this, similar to the square root. And of course, when I plug in x equals 1 to the third root of x, I get back to 1. So y starts on this third root of x and goes up to y equals 1, this straight line. So this is my region of integration right here, this little wedge. So that's our region of integration. What I'll do now is I'll change the limits of integration. So let's draw this region again. Instead of doing these vertical lines over here, let's draw the same region over here. We'll represent it a different way. That's x equals 1. That's y equals 1. And so what we'll do now is we'll say that y goes between 0 and 1. So now my y limits of integration, so y goes between 0 and 1. We can write our region R as a set of points x and y, such that y goes between 0 and 1. And now let's figure out the range of x. Well, as y goes between 0 and 1, x starts along this line over here. And what is that line? That line is along the y-axis, so that line says that x starts at 0. So x starts at 0. And goes up to this curve over here. What is that curve? That curve, as we know, is that y is equal to the third root of x. If I solve this equation for x, we get that x is equal to y to the third power. So we know that x goes between 0 and y to the third power. And now we've written this as a type 2 region. This is a type 2 region. The starting problem was a type 1 region. So now as a type 2 region, we can write this as the integral. Now we know that y goes between 0 and 1. Those are my y limits. X goes between 0 and y cubed. Those are my x limits. Then I have e to the y to the fourth dx dy. And now if I do an x integration, an x partial integration as an iterated integral, this becomes the integral from 0 to 1. And then I'm going to have an x times e to the y to the fourth, evaluated from x equals 0 to x equals y cubed dy. And this will just turn into the integral from 0 to 1. When I plug in y cubed, I'll just have a y cubed e to the y to the fourth dy. And now we can see that I'm missing a 3 over here, so we can make a u substitution. If we let u be y to the fourth, then du is 4y cubed dy. And so this integral will turn into what if I make this substitution over here? This integral is going to turn into the integral. Well, when y is equal to 0, u is equal to 0. When y is equal to 1, u is equal to 1. So I still have the integral from 0 to 1. Then I have a y cubed dy. That's a du over 4. So I have a du over 4. Then I have an e to the u. Well, that's easy. This is going to be 1/4. Then e to the u. And then u goes from 0 to 1. So this will be 1/4 e to the first power over here minus e to the 0, but e to the 0 is equal to 1. So this is 1/4 e minus 1, and that is your final answer. So by changing the region from a type 1 region to a type 2 region, we were able to actually compute the double integral or the iterated integral. Thank you very much.